All right, section 2, properties of water. If you look at the Earth, there's a whole lot of water on it, so it's kind of important to us. The structure of water. We talked about this in the last section a little bit. It's a polar molecule. The charges are not equal across the whole molecule, and that makes it form bonds with other molecules, including other water molecules. So it gives it lots of special properties. It's one of the few compounds that's liquid most of the time. It is a neutral molecule, but the charges are not evenly balanced. So one part of it is negative and the other part is positive, but overall it's neutral. So that's what the water molecule looks like. The side with the oxygen is more negative, the side with the hydrogens is more positive. The way the electrons are shared make it at this weird angle. The electrons are usually closer to the oxygen than the hydrogens, which creates that charge. Okay, so a hydrogen bond. Because these hydrogens have a positive charge and the oxygens have a negative charge, that can cause them to be attracted to each other. So just a hydrogen bonding to another atom is called a hydrogen bond. A water molecule can form lots of different hydrogen bonds because of these two hydrogens, and then other hydrogens can stick to the oxygen, so it can be like a big clump of water molecules. Cohesion, an attraction between molecules of the same substance. Water is really cohesive. If you spill some water on the table, it's probably going to stay in drops and not just individual molecules spread out all over the table. That's also what causes surface tension. That's why some little bugs can walk across the surface of water. That's why we usually use soap when we're washing something, because it reduces the surface tension, so you can actually get it clean. Adhesion, attraction between molecules of different substances. A good way to remember the difference between adhesion and cohesion. Adhesive bandages stick to your skin. That's how I remember it. It may or may not help you. A good example of adhesion: if you put some water in a graduated cylinder, look at it very carefully, the surface of the water is going to be curved. It's called a meniscus, because the water molecules are sticking to the side of the graduated cylinder more. The attraction is stronger than the forces that are holding the water molecules together. Capillary action. This is another example of adhesion. This is how water gets from a plant up into the stems and leaves, or from the roots up into the stems and leaves. Because as the water rises, cohesion is going to keep the water together. So basically, this water molecule is going to stick to the water molecule below it. So as this one goes up, the next one's going to follow. And then cohesion is going to keep it stuck to the sides of the tube, so it's not falling down. It's going against the forces of gravity, basically. Heat capacity, another property of water. How much heat energy it takes to increase the temperature. Water has a high heat capacity. That's why it takes a really long time for a lake or a pond to get nice and warm in the summer, because it has a high heat capacity. It's also why it takes a while for it to cool off. Right, another property of water, the fact that it's polar makes it able to dissolve a lot of other compounds. Water's not always pure. very seldom actually. Tap water is not pure water. Water in a pond, in a stream, whatever, probably not going to be pure water. It's usually a mixture. So composed of two or more elements or compounds that are physically mixed together but not chemically combined. So lots of mixtures involved in living things. Two types, solutions and suspensions. So a solution would be like salt water. The sodium and chloride ions separate from each other, but they don't actually chemically combine with the water molecules. So because the ions are mixed up in the water, it's called a solution. A solution is evenly distributed. It's got two parts, the solute and the solvent. Water is the solvent. What's the solute is getting dissolved in. We typically refer to water as the universal solvent because lots and lots of things can dissolve in it. In the case of salt water, the salt is the solute, the thing that's getting dissolved. Again, lots of things can dissolve in water. If it has all of the solute it can possibly hold, then the solution is saturated. Suspensions. So this is where the solute, which it's technically not a solute if it's a suspension, but whatever is getting mixed into the water is not going to be dissolved. Acids and bases. So it's pretty important for your cells to keep a constant pH. If the pH changes too drastically, you're probably going to be in a hospital. That's a problem sometimes for diabetic people. Buffers. I can't remember if they give you a definition of a buffer. Basically, a buffer is just a substance that keeps the pH from changing a lot, even if you put something with a higher or lower pH in it. So you'll use those a lot in chemistry. Your blood has a lot of buffers in it. So if you drink some vinegar, it's not going to drastically change the pH of your blood. Water molecules split apart to form hydrogen and hydroxide ions. There's a chemical equation. Pure water, about 1 in 550 million molecules will split up like this. The pH scale measures the concentration of hydrogen ions in a solution. It goes from 0 to 14. Hopefully you've seen this before. pH 7, the hydrogen and hydroxide ions are equal. If it's lower than 7, it's going to be acidic. If it's higher than 7, it's considered to be basic. Acidic things have more hydrogen ions. Basic things have more hydroxide ions. Each step of the scale is a factor of 10. So if you're going from 1 to 2, that's taking it times 10, basically. Again, acid forms hydrogen ions. And base forms hydroxide ions. Okay, so here's where they give you the definition of buffers. Weak acids or bases that can react with strong acids or bases to prevent sharp, sudden changes in pH. So if you put something into your body that's a big difference in pH from your blood, buffers will prevent, to some extent, how much the pH of your blood is actually going to change. Obviously, that's not 100%. There are cases where the pH of your blood is going to change depending on what it is you're putting in your body or if you have some sort of medical problem. So this is basically just demonstrating how a buffer works. So they're pouring an acid into this unbuffered base, makes it acidic. And then in this On this side, they're pouring acid into a base with a buffer in it, and it just changes the pH a little bit. And my slide won't go. Maybe because that's the end. So that's water. Has a lot of kind of cool properties. Hopefully, a lot of this is review from physical science. But water's kind of cool, kind of important to us, very important to all living things.